In this lecture, let us start with the convolution of Fourier transform. If you remember, we defined the convolution of Laplace transform and the properties of the convolution of two functions, and using the convolution properties, we were able to find out the Laplace transform of various functions. Similar type of thing we will do here. First, we will define what is the convolution of two functions, and then we will see some property of convolution of Fourier transform. If two functions are given to us, that we have two functions f x and g x, and as you know, the convolution of these two functions can be defined like this: f star g of x, this is equals to, here it is little different, it will be 1 by root over 2 pi minus infinity to infinity, we are just writing it into f t into g of x minus t dt. So, please note that the convolution, if two functions are given to us, that is f x and g x, then the convolution of two functions is defined as f star g of x equals 1 by root 2 pi minus infinity to infinity f t into g of x minus t dt. And on the same way, we can find out the convolution of Fourier cosine or Fourier sine transform also. So, I think it is okay that convolution of two functions f and g we define like this way. Let us see this one. The convolution of these two functions f and g is defined as this. Now, let us come to a theorem. The Fourier transform of convolution. Now, I am trying to find out the, just like Laplace transform, the Fourier transform of convolution of two functions, what will happen? What we are saying? The Fourier transform of convolution of f x and g x is the product of their Fourier transform, or in other sense, Fourier transform of f x star g x is nothing but f of alpha into g of alpha, where f of alpha is the Fourier transform of f x and g of alpha is Fourier transform of g x. So, this is similar to the Laplace transform also. In Laplace transform also same thing happen, that Laplace transform of convolution of two functions f x and g x, which is f star g equals Laplace transform of f x into Laplace transform of g x. In the same way, here also the Fourier transform of convolution of two function f x and g x, that is Fourier transform of f x star g x, which is equals to the Fourier transform of f x into the Fourier transform of g x. So, we will go through the proof of this one now. The Fourier transform of f star g, this equals, from the definition we can write down 1 by root 2 pi minus infinity to infinity f star g of x into e power I alpha x into dx. So, that it will be a function of alpha. So, you see here from the definition, just we are writing this is equals 1 by root 2 pi minus infinity to infinity f star g of x into e power I alpha x. Now, I know what is f star g, already we have defined. So, that you can write down 1 by root 2 pi minus infinity to plus infinity f star g is nothing but 1 by root 2 pi minus infinity to infinity f t into g of x minus t dt, g of x minus t dt, and this into dx. Now, without changing the property, we can interchange x and t parameters, or in other sense, this equals, you can write down 1 by root 2 pi, I am keeping it as it is, minus infinity to infinity. If I change the order of these two terms, then dx will come first. So, that f t I can bring outside the given integral. So, f t I am keeping outside root over 2 by pi minus infinity to infinity, sorry, here I have missed one term, that is this will be e power I alpha x into dx. This term will come here, which was there earlier. So, after bringing f t outside by changing the order of the integral, this you can write down g of x minus t into e power I alpha x into dx into dt, I can write down. And once I am writing this 1 by root 2 pi minus infinity to infinity f t. Now, you see what is this function 1 by root 2 pi minus infinity to infinity g of x minus t into e power I alpha x dx, which is nothing but we can say that Fourier transform of g of x minus t. From the definition of Fourier transform, the Fourier transform of g of x minus t is equals to 1 by root 2 pi minus infinity to infinity g of x minus t into e power I alpha x dx. So, if I am replacing this, it is nothing but Fourier transform of g of x minus t into dt. Now, this Fourier transform of g of x minus t, if you remember theorem 2 of shifting theorems, whenever we have done the properties, we have seen that this particular Fourier transform of g of x minus t is equals to, you can write down. So, I am just writing Fourier transform of f star g, this is equals 1 by root 2 pi minus infinity to infinity f t into e power I alpha t into g of alpha dt. This I am writing from the property that Fourier transform of g of x minus t, this is equals to e power I alpha t into the g of alpha, where g of alpha is nothing but the Fourier transform of the function g x. So, using the second shifting property, which I know as this one, I am replacing this Fourier transform of g x minus t equals e power I alpha t into g alpha into dt. Now, this g alpha is a function of alpha only, it is independent of t. So, that this g alpha I can bring it outside. So, I can write down 1 by root 2 pi into g alpha is coming here into minus infinity to infinity f t e power e I alpha t into dt. And this one 1 by root 2 pi minus infinity to infinity f t into e power I alpha t, this is nothing but. So, this is actually g alpha into 1 by root 2 pi minus infinity to infinity f t e power I alpha t, again is nothing but f of alpha, means which is the Fourier transform of f and g. So, I can write down this is equals f alpha into g alpha, which completes the proof of this one, that Fourier transform of f star g is nothing but Fourier transform of alpha, sorry, Fourier transform of f x into the Fourier transform of the function g x. So, this completes the proof. From here, one corollary we can draw, that is, we can say Fourier inverse of f of alpha into g of alpha, this is equals to then f star g of x, because we got Fourier transform of f star g of x equals f alpha into g alpha. So, Fourier, from there I can write down Fourier inverse of f alpha into g alpha, this is equals to f star g into x, and this is equals, I can write down Fourier transform of f alpha convolution Fourier inverse of g alpha. So, this corollary we can obtain that Fourier inverse of f alpha into g alpha is equals to Fourier inverse of f alpha convolution Fourier inverse of g alpha. So, just let us see the proof of this. I have written this Fourier transform of f star g as 1 by root 2 pi minus infinity to infinity f star g of x into e power I alpha x, which is equals to your, if I use here this f star g, I am writing in the form of using definition 1 by root 2 pi minus infinity to infinity f t into g of x minus t dt. Now, the change the order of the integration means first I will, without changing the property of the integral, x will come first. So, that I can write as f t will go outside, f t into 1 by root 2 pi minus infinity to infinity g of x minus t into e power I alpha x into dx dt, and this integral is nothing but I can write it as this one f t into this integral 1 by root 2 pi minus infinity to infinity g of x minus t e power I alpha x dx is nothing but Fourier transform of g of x minus t. Now, you use the second shifting theorem 2 of the shifting property, and you can write down this Fourier transform of g of x minus t as e power I alpha t into g alpha dt. So, that g alpha is independent of t and g alpha can be being outside the integral. So, that g alpha into 1 by root 2 pi minus infinity to infinity f t into e power I alpha t dt, and this integral is nothing but f of alpha Fourier transform of the function f x. So, this completes our proof that Fourier transform of f star g equals Fourier transform of f x into Fourier transform of g x. And from here we can draw this corollary Fourier inverse of f alpha alpha into g of alpha equals Fourier inverse of f alpha convolution Fourier inverse of g of alpha. Now, let us see the application of this convolution on evaluation of the Fourier transform. Let us see one example. A function f x is given, that is e power minus a x, where a is greater than 0. From here we want to find out the Fourier sine transform of e power minus a x, and once I am finding the Fourier sine transform of e power minus a x, I also want to evaluate the value of the integral 0 to infinity alpha sin alpha x by a square plus alpha square into d alpha. Let us see the example. So, I have to find out first Fourier sine transform of e power minus a x, where a is greater than 0, root over 2 by pi 0 to infinity e power minus sin a x into sin of alpha x dx. And if you remember, we have done already, we have solved this problem, that what is the Fourier sine transform of e power minus a x. So, I am not going through this, please see the earlier lectures where we evaluated. I am just directly writing the value as root over 2 by pi into alpha by alpha square plus a square. So, please note that I am using the already used property, already solved problem, because we obtained the Fourier sine transform of e power minus a x earlier, and using that value we are obtaining the value as alpha by alpha square by a square. And if you remember now, I have to find out or evaluate this integral alpha sin of alpha x by alpha square plus a square into d alpha. I have to find out the value of this. If you note this thing is common. Fourier sine transform of e power minus a x is alpha by alpha square plus a square, which I have obtained over here. And so, therefore, from common sense I can tell that if I take the inverse Fourier transform, I will obtain this integral effectively alpha by alpha square plus a square into sin of alpha x. So, by inversion formula we can write down f x equals root over 2 by pi 0 to infinity root over 2 by pi into alpha by alpha square plus a square into sine of alpha x into d alpha. That is, you are getting this thing using the inversion formula from here. F x you can write down root over 2 by pi 0 to infinity root over 2 by pi alpha by alpha square plus a square into sine of alpha x dx. And you know your f x is already given, that is e power minus a x. So, I am substituting the value of f x over here as e power minus a x, and this integral will be 2 by pi 0 to infinity alpha by alpha square plus a square into sine of alpha x d alpha, sine of alpha x into d alpha. So, once I am getting this, therefore, the value of the given integral, that is 0 to infinity alpha sin alpha x by alpha square plus a square d alpha will be nothing but pi by 2 into e power minus a x. From here we can write down. So, just I am writing this, therefore, 0 to infinity alpha sin of alpha x by a square plus alpha square into d alpha. This is equals to pi by 2 into e power minus a x. So, please note that I know the value Laplace transform of a particular function. From that function I am using that property, and then using the inversion formula I am evaluating or I am finding the value of the given integral. Let us see here. So, Fourier sine transform of e power minus a x is equals to root over 2 by pi 0 to infinity e power minus a x into sine of alpha x dx, and I know the value of this, that is 0 to infinity e power minus a x sin alpha x dx value will be alpha by alpha square plus a square. As I repeated earlier, this problem we have solved earlier. So, please go through that lecture if you have forgotten that thing. So, once I am obtaining that by inversion formula, now I can write down f x equals root over 2 by pi 0 to infinity root over 2 by pi alpha by alpha square plus a square into sine of alpha x d alpha. So, that your f x is given as e power minus a x. So, e power minus a x equals 2 by pi into given integral. So, that the value of the given integral, that is 0 to infinity alpha sin alpha x by a square plus alpha square into d alpha is nothing but pi by 2 into e power minus a x. Now, let us see the next problem. This is the other one, on the same tone we will do it. The function is same e power minus a x, but here I want to find out the Fourier cosine transform of e power minus a x, and from there I want to find the value of 0 to infinity cos of alpha x by a square plus alpha square into d alpha. So, obviously, now you have understood that the technique will be similar as we have done it in the case of the earlier problem. That is, first I will find out the Fourier cosine transform. Again, if you remember, we have done already what is the Fourier cosine transform and Fourier sine transform of e power minus a x earlier. So, I will use that particular value whatever we have done earlier, and using that one we will try to evaluate the value of the given integral. So, following the same thing as we have done earlier, Fourier cosine transform of e power minus a x equals to root over 2 by pi 0 to infinity e power minus a x into cos of alpha x into dx, and this value here it is. In the earlier case for sine it was alpha by alpha square by a square. If you remember, here the change will be only a by alpha square plus a square. So, Fourier cosine transform of e power minus a x is nothing but root over 2 by pi a by alpha square plus a square, and this value, this evaluation we have done earlier. So, you can use that thing, you can go through that lecture. So, that using inversion formula from here I can write down f x equals root over 2 by pi 0 to infinity root over 2 by pi into a by alpha square plus a square into cos of alpha x into d alpha. So, that you can write down e power f x is e power minus a x. So, it will be 2 by pi 0 to infinity a cos of alpha x by alpha square plus a square into d alpha. Therefore, you can write down 0 to infinity cos of alpha x by alpha square plus a square. This is nothing but, so this a will be coming here. So, it will be pi will go up in the denominator, there will be pi by 2 a into e power minus a x. So, therefore, the value of the given integral 0 to infinity cos of alpha x by alpha square plus a square, this is equals to pi by 2 a into e power minus a x. So, let us see here Fourier cosine transform of e power minus a x is nothing but root over 2 by pi 0 to infinity e power minus a x into cos of alpha x dx. Using this one, we are obtaining the value using the earlier value. We can write down the value of the given integral as a by alpha square plus a square. And once I know Fourier cosine transform of the function, using the inversion formula, I am finding out f x equals this value, and therefore, f x is e power minus a x. So, this equals I can write down 2 by pi 0 to infinity a cos of alpha x by a square plus alpha square d alpha. So, that the value of the given integral, that is 0 to infinity cos of alpha x by a square plus alpha square into d alpha equals pi by 2 into e power minus a x. Now, let us see the Parseval's identity or theorem, whatever you say, same thing we did for the Laplace transform also. So, if capital F of alpha is the Fourier transform of f x, where f x is a complex function, then minus infinity to infinity modulus of small f x whole square dx, this will be equals to minus infinity to infinity modulus of capital F alpha whole square d alpha, where f alpha is nothing but the Fourier transform of f x. Let us see the proof of this theorem. So, we are starting from the right hand side, minus infinity to infinity modulus of f of alpha square d alpha. So, this equals, I can write down this modulus of this, I can write f alpha into mod of this into d alpha, and this equals minus infinity to infinity f of alpha mod over there, and this f alpha is nothing but Fourier transform of f x. So, from definition I can change it as 1 by root 2 pi minus infinity to infinity f x into e power I alpha x dx into your d alpha will come. So, this equals, now if I change the order of the limits, that means first integrate with respect to alpha, then integrate with respect to x, then f x will come outside, f x into 1 by root over 2 by pi minus infinity to infinity f of alpha over mod into e power I alpha x d alpha into d x. So, this again this equals to minus infinity to infinity f x into 1 by root 2 pi minus infinity to infinity. This mod I can bring e power I alpha x also. So, it will be e power minus I alpha x if I make the mod over here into d alpha into d x. And what is this? 1 by root 2 pi minus infinity to infinity f of alpha into e power minus I alpha x. This is nothing but your f x is there and this is f x bar dx. So, therefore, what is happening? Please note that f of alpha, mod of f alpha is there, f alpha bar was there into not mod, f alpha bar into e power I alpha x was there. This I am writing as f alpha into e power minus I alpha x whole bar, I am just writing over here. And this integral is nothing but 1 by root 2 pi minus infinity to infinity f alpha into e power minus I alpha x d alpha is f x bar only. So, that this equals minus infinity to infinity f x bar whole square. So, this is again minus infinity to infinity absolute value of f x whole square into d x. Please note that this completes the proof of our theorem that minus infinity to infinity the mod of capital F alpha whole square d alpha is equals to minus infinity to infinity mod of f x whole square d x, where capital F alpha is nothing but the Fourier transform of f x. So, let us see again, this was the theorem we had to prove that if f alpha is the Fourier transform of the given function f x, then minus infinity to infinity mod of f x whole square d x equals minus infinity to infinity mod of capital F alpha whole square d alpha. So, we are starting from the right hand side, that is minus infinity to infinity mod of f alpha whole square d alpha. This mod of f alpha whole square d alpha I can break it into f alpha into f bar alpha. So, that only I am writing f alpha into f alpha bar. Now, f alpha bar is there. What is f alpha? I know f alpha is nothing but the Fourier transform of f x, and from definition I am writing it as 1 by root 2 pi minus infinity to infinity f x into e power I alpha x d x into d alpha, using the definition of capital F alpha, that is Fourier transform of f x. Now, without changing the property of the integration, I can interchange the order of the integration. So, by changing the order of the integration, f x can come outside, and this I can write down 1 by root 2 pi minus infinity to infinity f alpha bar into e power I alpha x. Now, this f alpha bar into e power I alpha x, I can bring it together and I can write down f alpha into e power minus I alpha x whole bar, I can write down. So, that if I break it, then again I will get back the earlier one. And if you see, this is this integral 1 by root 2 pi minus infinity to infinity f alpha into e power minus I alpha x d alpha. This is actually the inverse Fourier transform of f x bar. This integral is nothing but the inverse Fourier transform of f x bar. So, that you can write it as f x into f x bar d x, and this f x into f x bar nothing but mod of f x whole square. So, that we complete the proof as minus infinity to infinity mod of f x whole square d x, this equals minus infinity to infinity modulus of capital F of alpha whole square d alpha, where capital alpha is nothing but the Fourier transform of f x.